So good morning, everybody. I'm very honored to be here this morning. And I have a very difficult task to speak about energy, which is a very complicated issue, in 45 minutes. And I try to do my best to fulfill this very complicated goal. First of all, I would like to thank Professor Cole Hamilton for this invitation, the president of UCAMS. I would like to thank Professor Riccio, the president of the Italian Chemical Society, as well as Professor Zingales as president of the Consiglio Nazionale dei Chimici. And I also would like to thank Professor Sergio Facchetti, because I'm sure that he is responsible also for me to be here this morning. Thank you very much, Sergio. And I would like also to thank Professor Gino Ambrosio, the president of the department of the CNR I belong to. And now I would like to start with my talk. This is the outline. Oh, sorry. I need this. Okay. So this is the outline of my talk. Very simple. I will speak about the present situation of the energy system in the world, the perspectives. And finally, I will devote some reflections to Europe, since it is the scope of the today meeting. Sorry, one more technical. Okay, thank you. Okay. So, of course, I will start from the present situation, okay? I think it is very useful to have a look at the so-called energy timeline and see how much has been the energy consumption over the history of civilization that dates back to 5,000 years ago. And the energy consumption was very, very low for a long time. And energy came essentially from muscular force, from animals and human beings. And then the massive exploitation of fossil fuels started some 150 years ago, and the energy consumption increased dramatically within a few generations. And still more than 80% of the energy, of our energy supply, comes from fossil fuels. And in Italy, it is more than 90% indeed. And the big question now is, can this last forever? Because living here, the quality of life is amazingly higher compared to here. The standard of living of a regular citizen now is much bigger than one of a Roman emperor at that time. And we know that the answer is no, it cannot last forever, just because the fossil fuels are going to be depleted during the present century. So we have a big question mark to answer. And we are running too fast in consuming fossil fuels, and I think this can be exemplified by these numbers. Presently, we extract from the Earth about 10 gigaton of fossil carbon every year. And to make this available, it needed paleobiomass at the era of the dinosaurs of 50,000 gigatons that was transformed through millions of years. And to harvest these 50,000 gigatons of paleobiomass, it took approximately 500 years. So we are now presently consuming in 1 year what was harvested by the sunshine in 500 years, and through millions and millions of years of time, of geological time to be worked out. So we are clearly running too fast. Another number that shows us that we are running too fast is the following. This is the energy consumption of the two biggest economies in the world. Now number one is China with 2.8 gigaton of energy every year. This is primary energy. This is the total per year. But this is not the interesting number to look at. The really interesting number is this one. If we look at a per capita level, the average Chinese still consumes 3.5 times less energy than the American average citizen. Therefore, if the average Chinese would consume 7.3, since Chinese are 1.3 billions and Americans are 320 millions, this column here would be 4 times higher. So it would go up to the second, maybe to the third floor, okay? And we can make the same kind of considerations about India, about sub-Saharan Africa, and so on. So it is clear that we cannot continue along this pathway. Another interesting number to look at is who is the owner of the oil reserves on the planet. And the last data show that these are the top 5. And as you can see, 62% of the world reserves are concentrated in just 5 countries. But on this planet we have 200 countries, so it is a highly concentrated energy resource. And that's make a series of problems. And gas is even more concentrated than oil. And the problem is that there is a place which is indicated by that ellipse, which is the most dangerous place on Earth. And it is not by chance that in this place there are 16 countries which own 70% of conventional oil and gas reserves. So all the wars and the tensions in the last maybe 70 years have been exactly in this place, even right now, or in the surrounding nearby places. So oil and gas are making our world a very insecure one. Energy is not only the energy that we use every day, like the one I'm using to use that projector, but also the energy is embedded in every item we use, even in the chair that you are sitting on right now. It took energy to make it. So these are some numbers that show how much energy has been used to make some stuff. For example, for aluminum, it takes 4.2 tons of oil in terms of energy to make 1 ton of aluminum. That's why we have to recycle it. And this is the number for plastic and steel. These are sort of pillars of our civilization right now, plus including cement. And then even in items, let's take the motor vehicle. To make 1 ton of a car, it takes 2.4 tons of oil equivalents in terms of energy to make it. Therefore, a car has consumed a substantial part of its energy of the entire life cycle before running a single kilometer on the road, approximately 50%. And this is true also for food, because today we have to speak about food. To make food available on your table, it takes a lot of energy, and the highest value is for greenhouse vegetables, and this is pretty intuitive. And on average, to make 1 kilo of greenhouse vegetables, the vegetables we are going to eat from now till the next spring, it takes approximately 1 kilo of oil in terms of energy to make it available. So someone says that we believe to eat food, indeed we eat gas and oil, and that's somehow true, okay? And energy and food are strongly related. And I want also to point out something else about food, showing that energy is also wasted everywhere. Wasted, too much. 10% of the US energy supply is used to make food available in terms of agriculture, in terms of conservation, transportation, and so on. However, that's very terrifying. Approximately 25% of the American food is wasted before feed anyone. So this means that 2.5% of US energy supply is wasted in food loss. And this is a gigantic number because the US are big energy consumers. If you want to have a pictorial picture of this, I found it a few days ago on the National Geographic. And this is the average US family surrounded by the wasted food throughout the year. So there is a lot of pork, beef, poultry, fish, a lot of milk. That's wasted. This is for each and every single American family. Energy is also strongly related to water, and we can say that it takes a lot of water to make energy. This is the case of Europe. As you can read over there, 44% of the total abstracted water in Europe is for energy uses, and particularly to cool down thermal power plants. So without water, we cannot have even energy. So in order to have an idea of the energy bonanza that we are enjoying in this very moment of history, we can try to quantify this taking a naive power unit, which is the energy slave. Instead of using watts in an aseptic way, let's consider to consider as our power provider a person that is deploying muscular force for us for 8 hours, okay, which is the typical working day. And an average person, I'm not talking about an Olympic champions, an average person can deliver it between 50 and 80 watts, approximately, of power steadily for 8 hours. So let's say this guy is your hypothetical slave, the one pedaling for you continuously, at least for 8 hours. And what about Europe? and energy slaves. The average European citizen consumes 3.5 tons of oil equivalents, and you make your calculation on the paper, and you find out that it's like having 58 energy slaves working for us continuously 24/7 every single day of the year. This is true for every average European citizen. So we are really living a big energy bonanza, but we are very poor in energy in Europe. I will come back to this point later on. So one can say, okay, we are energy kings, but energy is very expensive, extremely expensive. First of all, let me note that 1 liter of gasoline, 1.6 euro right now, is still costing less than 1 liter of mineral water that I bought yesterday night at the restaurant. It is not less than 2 euro, okay? So, but I want to give you a more concrete example of the fact that energy is not so expensive despite our complaint. The average household electricity consumption in Europe is 3,500 kilowatt hours. The electricity consumption for lighting, which is a very important service that we have, now we give it for granted. You know, when the sunshine goes down, we just switch on the light and it's granted. But until 3 generations ago, at dusk, everything was stopped because it was not possible to continue to work. We can continue to do whatever we want by night. So it is an essential service for us. So this means that we consume less than 500 kilowatt hours of electricity in our household every year for this very essential service. How much does it cost? It costs less than 100 euro, much less than our phone services, for example. And this amount of energy corresponds to 766 slaves working for us for 10 hours. And if we should pay them at 30 euro per hour, the typical average cost of workforce, this should amount to 230,000 euros. So the difference between this number and this number, I would say, epitomizes our energy bonanza. That's why we are energy king compared to our ancestors. And the reason why we can have this standard of living, it is because the cost of energy is extremely low. We couldn't survive the present economy with a higher cost of energy. And you know very well that in the last 70 years, and particularly in the last 30 years, we have done worse to keep the price of energy low. Otherwise, our economy collapses in 2 weeks. But there is a problem. The main energy resource is conventional oil. Conventional oil is the oil that you drill, and spontaneously it comes out for years and years. This is conventional oil, what we studied at school. Unfortunately, the discoveries of conventional oil, the golden age of discoveries, is over. It was between the 30s and the 80s. And as you can see there, the gray bars are less and less over time. But the consumption continues to grow. So it is evident that we are going to, we are marching to a problem, as it was discussed in this very interesting special issue of the Philosophical Transactions of the Royal Society early this year. So we are entering silently in a different era. Nobody told us, but we are entering here in the era of extreme fossil fuels. Because we are going deeper and deeper in the ocean, we are trying to exploit resources in places which were not exploited previously, which are very remote and very expensive and very environmentally complicated. And we are starting to exploit unconventional hydrocarbons, and particularly tar sands and shale oil and gas. And let me tell you something about shale oil and gas, because it is a very hot topic, even discussed in Chemistry Journal continuously. To make it available, shale gas and oil, you have to make something which is the so-called hydraulic fracturing. So you drill in the conventional reservoir, you drill and nothing happens. Because the oil and gas is tightly attached to the layer of shale that traps it. So you have to make first horizontal drilling, and then you have to inject water at very high pressure, which contains chemicals and so on and so forth. And then finally, the oil and the gas goes back to the well and can be recovered on the surface. Scientists have demonstrated that this implies a lot of environmental problems. I gave you some references here, but I I don't have the time to discuss each of them. Let me just focus on the last two. There is a quickly declining rate of production. So what is the problem with shale oil and gas? That you drill, and then that well will be productive for, when you are lucky, 2 years. And then you have to take it away and drill in another place nearby. So of course it is much more expensive to keep on drilling continuously. In the biggest oil shale basin in Texas, 40,000 wells have been drilled in the last 9 years, which is an incredibly high number, which would be impossible to achieve in Europe, where the density of population is much higher than in northern Texas. So this is the problem. The other problem is that there is a poor energy return on energy investment. This is a very important concept that should become more frequently discussed even in the chemistry community. The concept is very simple. It takes energy to get energy. So, and I showed it with these two pictures. This is your favorite gas station, okay? It is obvious that to have energy available here, next to your house, starting from an oil well in another continent, perhaps in the ocean, it takes a lot of energy to make it available, okay? So the energy return in the US has been very high until the 1950s, about 100. So for energy unit invested in energy, you got 100 units in return. So it was a big rewarding activity, highly rewarding activity. In the 1970s, this number became lower, and it has been estimated it became 30, and nowadays it's below 10. And this is a very dangerous problem, because everyone can clearly understand when this number goes below 1, it is totally useless to try to have this oil, because it's just an energy wasting activity. But indeed, the dangerous number is much bigger than 1. It has been estimated recently by some financial analysts in London that the dangerous number is 10. Let me describe this slide. This showed that the ROA for a long time, until the 1990s, was very high. On average, on the planet, around 100. And the money that we invested as world economy to get this energy out was extremely low, extremely negligible. So it didn't affect the world economy. So we had almost, let's say, energy for free compared to the big machine of the world economy. But as the energy that you extract is less and less, and the energy that you have to invest to have this energy is increasing down here, there is a point after which there is a collapse. And they calculate that below 10, the economy, as we know, would collapse. And somebody is also arguing that probably our present economic crisis is the indication that we are approaching the ROA cliff. Just for your information, has been recently published the number of the ROA for the shale gas, the USA shale gas, which is 12, not very far from here. And for the oil, it is estimated to be 3-4, so it is much lower than that. And if you are reading, and you are certainly reading the newspapers, including the Italian one, it seems that this shale oil and gas is shaping as a sort of financial bubble. We will see in the upcoming months if this is true. So we have to be very careful when you talk about shale oil and gas, because definitely it's not conventional oil and gas. It's another story. Let's not make a comparison between, okay, we used conventional gas and now we can use shale gas. It's another story. It's a completely different story. Okay, we have some related big issues I cannot discuss, of course. The first one is that the world population is poised to increase again. We are now 7.2 billion, and we are going to get 9 billion by the mid of the century. And there is the big problem of global warming, which is induced by the injection of gigantic amounts of carbon dioxide in the atmosphere. And related to the use of fossil fuels, there is also environmental degradation. This is a very interesting picture taken a few days ago of the Po Valley, where I live, unfortunately for this, and which is typically full of particles and fogs as well in the fall and winter. So somebody says that we are approaching a perfect storm. I hope it's not true, but there are some signs that might be true. So to summarize this first part of my talk, in the last 8 years we lived the fossil fuel age. And this gave us the possibility of having a fantastic life, of feeding 7 billion people on the planet, having very comfortable houses both in winter and in summer, and traveling all across the planet in just 30 hours. And most of these advantages have been obtained thanks to chemistry. We have to highlight this, okay? However, we have to be aware that conventional hydrocarbons will be virtually impossible to replace. That age is going to finish. It's a limited period of human history, so we have to move forward now. So that's why I go to the second part of my talk, the perspectives. And the first question that we have to pose is how many perennial, let's call them, or renewable, it is more common, alternatives do we have? Not so many, but plentiful. We have solar energy, geothermal energy, and gravitational energy. Solar comes in several direct and indirect forms. And in order of decreasing character is the decreasing amount that we have and that we can exploit. So this is what we have. And what we have to make, coming from our brain, as it was mentioned before, we have to deploy the technologies that can exploit this huge amount of energy fluxes that is available to us from now and for the millions, thousands of generations ahead of us. The first question is, do we have enough? Yes, indeed. If we take the current primary energy consumption as 1, which is the reference, let's say, what we consume today, the big cubes represent the available potential on the planet, made available by nature, by several renewable fluxes. And the smaller cubes in front of them is the amount that is technically, economically, and ecologically exploitable now in the present technology. So if you make the summation of the small cube, it is much more than 1. So one could conclude, why don't we switch to renewables tomorrow morning? It's difficult. We know historically that energy transitions take a lot of time. The one from wood to coal, from coal to oil, and so on, and from oil to gas, it took a long time. And this transition will make no exception, because the energy system is a gigantic system now spread all across the planet, and it will take a lot of time and a lot of troubles to change it. But the good news is that we can change it. We can be powered by renewable energies. However, we have to be practical, because we are citizens working every day. So what do we need? We need 2 things. We need electricity and fuels. That's it. And presently, in the affluent world, about 1/4 of our final energy consumption is electricity, and 3/4 is fuels. And you can feel from here how imbalanced is typically the public debate, because when we talk about energy on the media, typically they talk about photovoltaics, nuclear, wind, but that's only electricity. You have to be careful about this, because 3/4 is fuel, because we heat our buildings with fuels, not with electricity in most cases. What is the difference between this and that? Electricity is extremely convenient to transport in a very efficient way through huge distances. But it is very difficult to store and very expensive, and still we don't know how to store it efficiently. The fuels is the opposite. It can be stored for a long and indefinite time. If you have a gasoline tank over there, in 100 years you come back, it's still there and you can use it. And this is completely different compared to electricity. But it's more difficult to transport, and it is also more dangerous to transport. So they are, also in this sense, they are complementary. So due to this, we have, in perspective, 2 objectives: to produce electricity, to produce fuels with perennial, renewable energies. That's what we have to do. And thirdly, but last but not least, reduce consumption in the affluent world and increase the efficiency. So now I will go one by one through these points very quickly, of course, but just to examine each of them. The first one is target electricity. We have just to consider that it is obvious, it is the reality that the most mature renewable technologies are electric. So a most desirable trend would be to increase the share of electricity in the final end use. We are at 25, let's move to 30, 40, 50, and maybe 60. And that trend is already starting, has already started a long time ago, and is moving strongly now because, as you can see, there are an increasing number of companies proposing electric models because the big amount of fuels is used for transportation. So shifting from transportation from fuels to electricity would be a big change, okay? An epochal change. However, one could say, well, there are more than 1 billion cars on the planet. It would require a lot of electricity that we don't have. That's not true. Let me show you why. How much electricity is necessary to power an electric car? I took as an example this very powerful and luxury car, American one, the Tesla, maybe you know it. And the consumption of this car, it is only electric, it is not hybrid, is 0.18 kilowatt hour per kilometer. I personally drive 15,000 kilometers per year, so if I would have this very expensive car, I cannot buy it indeed, at the moment, but they are making a cheaper model shortly, and maybe I can buy it. And I would consume 2,700 kilowatt hour in 1 year. Is it much or not? Not too much. Because it is exactly the consumption of my household. We are 5 people in my family, and this is our electricity consumption. So by doubling my electricity consumption, I could drive the entire year this very luxury car with electricity. And I would save a lot of money because electricity is much cheaper than fuels. So let's expand this calculation to Italy. We have 37 million cars. The average mileage is this one, 12,000 kilometers per year, which means that to power all the Italian cars, there are a lot of cars in Italy, you know that. If you go outside here in Rome, there are an amazing number of cars. Well, to power all of them, we would need 80 terawatt hours. I'm making calculation with a luxury car, not an economy car. So I stay on the safe side, let's say, okay? So is it too much? Well, not too much, because in Italy last year we produced 112 terawatt hour only from renewables. So the message here is that, which is the 40% of the total. So the energy transition is already happening, by the way. Anyway, if we use with 70% of the only production of renewable electricity, we could power the whole, all the Italian cars for 1 year. So it is doable. It is clearly doable. So let's be prepared, because this will probably happen. This will probably happen because the amount of electricity which is produced by renewables is increasing. The wind energy power, the deployment of power of wind energy has been increased dramatically in the last 18 years. And presently, last year, the end of last year, wind produced 3.3% of the world electricity production, which means that wind is the candidate to replace nuclear energy, which is in a dramatic and probably final crisis due to economic reason, and not only. So presently, the wind produces the amount of the corresponding amount of 85 nuclear or coal power plants. What about photovoltaics? Photovoltaics was even faster in the last few years. And presently, at the world level, at the end of last year, it corresponds to 23 conventional power plants of 1,000 megawatts. But the very good news showing that it's not true that Italy is always at the end of every ranking, important ranking in Europe. Italy is the country that produces most electricity from photovoltaics in the world right now. Last year, we produced almost 8% of our electricity needs from sunshine, which is an amazing number. Nobody could have guessed this 10 years ago. So we are really at the beginning of a revolution. All of this is silicon, of course. You know that, at least in Europe. There are potential competitors for crystalline silicon. Well, as chemists, we know that in the last few years, there are 4 technologies that showed up: organic, perovskite, DSSC, and amorphous silicon, which is an old one. And you see that in particular these two, and particularly the perovskite one, has had an impressive increase of efficiency in lab tests during a very few years. So it is possible that in the future the silicon will be integrated by other technologies, even though it will be very difficult to replace it. I would say impossible, because it is a very established technology, 60-year-old, and now it is extremely cheap. But I think that the biggest challenge for intermittent renewable is not the material. Maybe we can find new materials. We have other challenges for which chemistry is very important. We have the problem of overcapacity. So renewables work for between 10 and 50% of the time of the year, not up to 80% like nuclear or coal. So in order to have the same amount of electricity produced, you have to install 2, 3, 4 times as much to have the same amount of electricity released. There is the storage. At the peak time, particularly in Italy, in summertime, at midday, we have an excess of production of photovoltaic which is not properly stored because we still don't have the technology. So there is a lot of work to do in the storage of electricity, and that's chemistry, of course. And the other problem is the electric grid, which has to be completely reshaped. The present grid was designed approximately 1 century ago. It is expected to deliver huge amount of electricity produced in very small, in a very limited number of places, the power plants. But we are going in the opposite direction. Little amount of electricity produced in countless places like your roof. The second point, target fuel. Here, what is going to happen is a change of paradigm. Because so far we have exploited naturally occurring fossil fuels, but we need to move to the manufacturing of fossil fuels. So the fuels of the future will be produced at an industrial plant. It will not be extracted and just worked out at a refinery. So this is a big change. This situation is really a big changer. We already harvest solar energy through natural photosynthesis, through biofuels. And these are some numbers which can be interesting. And we are already working at the first generation. These are already available, bioethanol and biodiesel. And you know that there are big problems. For example, in the United States, almost 40% of the corn that is produced goes to the production of ethanol. The energy return here is very poor. That's another problem. But it is clear that this model cannot be exported everywhere. So definitely this is not the model for Europe. We don't have land enough. We have to feed 500 million people. And now we are moving to the second generation biofuels, and bioethanol is now possible to be made through cellulosic materials on non-food crops. In Italy, we are at a very advanced stage in this regard. There is a very important plant, one of the first in the world in Piemonte, and this is coming up. That's good. Again, this is chemistry. Chemistry can offer a solution. And now we are moving possibly towards the third generation of solar fuel, which is artificial photosynthesis. In a schematic way, the idea is to take abundant molecules and transform them in fuels like hydrogen or methanol. This cannot be done directly, as we chemists know, unfortunately. So we need artificial intermediation through materials, processes, systems that help us to make this. And the classical option, the best option, is water splitting. So to take water, to split it with sunlight, which cannot be done directly because this doesn't absorb so much of the sunlight. Anyway, and so here you need this. And then you can have hydrogen and oxygen. And when you have hydrogen, you can do a lot of things. We know as chemists. You can use it as a fuel or as a chemical. And when you use hydrogen, typically you oxidize it. So you go back to the starting point. So the exhaust is also the starting material. And therefore, this is the beginning of a circular economy, which is the only economy that can work on the long term. The water splitting requires some key components, which are schematized in this slide, which is very simple. It can be a photoelectrochemical scheme, but this is the simplest one. So you need an antenna that absorbs sunshine. The antenna can be done in the lab, of course, hopefully, or can be taken even from nature in a hybrid approach. You need a charge separation module, and you need a catalyst for hydrogen evolution and oxygen evolution on the two sides, separated by a membrane which keeps the proton going in one direction. So every and each of these fields is a very important field of chemistry nowadays. And for example, in our lab, we have been working for many years in this area of the antenna and charge separation modules. Let me give you just one of the recent examples that we have worked out. It's this supramolecular model photosynthetic antenna charge separation system. We took a fullerene hexasubstituted fullerene with 12 porphyrins around it, zinc porphyrins. They absorb a lot of the visible spectrum. They are 12. And this zinc porphyrin is able to link another incoming fullerene with an imidazole unit here. This is just a spectator because it is hexasubstituted. The electronic properties of this make it possible to have an electron transfer in this direction. So this is a real model of the photosynthetic reaction center. And there are a lot of work ongoing, not only in our lab, of course, but in many, many labs across the world in trying to make some artificial systems like this. And now let's come to the last point, which is the target reduced consumption and increased efficiency. And this is a delicate question, because one can wonder, well, reducing consumption, but how much? Let me demonstrate you how much through this diagram, which plots the infant mortality, which is a parameter strictly related to the quality of life. The lower the infant mortality, the better the quality of life. And as you can see, you have very high infant mortality when the energy consumption per capita per year, which is plotted here, is low. And then when you increase the energy consumption, the infant mortality goes down, which is, of course, what you expect. But what is nice to see in this diagram is that there is a point, approximately at 2.8 ton of oil equivalent per person, that there is no more improvement in this parameter of the quality of life. And you can plot maybe 50 parameters, similar parameters describing the quality of life, and the trend is more or less the same. So the take-home message of this slide is, above 2.8 ton of oil equivalents, it is only energy wasting, and it is stupid to go beyond that level. And that's important for the politicians to know, that we do not have to increase the energy consumption indefinitely. There is a limit after which it makes no sense. So I made some calculations by myself, and I said, okay, now the world energy consumption divided by the number of people gives that each of us consume 1.8 on average on the planet right now. So we are below 2.8 because there are a lot of energy poor people. And if we target 2.8 by mid-century, when we will be 9 billion, this would amount to this number. So approximately you can say that by doubling the energy consumption by mid-century, we could give energy dignity to everybody on the planet on average. What is the present situation? Well, China is still below. It is the biggest energy consumer, but it's still below this level. There are many countries which are at an acceptably high level. It is clear, it is evident that the Northern American countries, we have to reduce their consumption. Of course, Canadian can be above 2.8 because it is a very cold country, but 9.4 is something that is clearly unacceptably high. And even EU is higher. In fact, EU has the objective of reducing energy consumption by 2020, by 20%, which makes exactly 2.8. So this means that we are not so far in these simple calculations. So Italy is not so bad. So a wise Italian prime minister should say, okay, let's stop here. Okay? In fact, we are even decreasing this due to European regulation. That's good. But there are many countries which are at an acceptable level. And you see Ethiopia is 0.03. And the question here is, what would you do with 0.03 ton of oil equivalent per year? Living with this amount of energy, the life is hell, is not life. And what would you do? You do this, and you do the same probably, okay? So by knowing the energy reality of our planet, allow us to understand what's happening on a larger scale, let's say, okay? About the efficiency, lighting. The present situation of lighting in terms of efficiency, the overall efficiency is the following. An average power plant produces with 40% efficiency from the primary input. So 60% is wasted on the river nearby as heat. And transmission is very efficient. Then when you get this input in your house, and it is, and you use this kind of device, this has a conversion efficiency of 3%. In fact, this is not a lighting device. This is a heating device, okay? And the overall efficiency of this process is less than 1%. This is not an energy system. This is energy madness. And that's why now it is prohibited to sell this kind of lamps, because this is a crime against the environment. We already have the technologies developed many, many years ago to have a higher efficiency, but we are still below than 10% with the fluorescent tubes. That's why what is happening, it's happening an ongoing epochal change in lighting. And we are moving from the old technologies, the so-called hot lighting, in which light is a secondary effect of an electric discharge, of heating, to system in which lighting, the cold lighting, is the direct effect. But to have the direct effect, you need a luminescent material That's why, again, chemistry is key to provide materials to the new lighting technologies. LED are point light sources, and OLED are flat light sources. OLED are very difficult to make. They are extremely demanding from the energetic point of view, from the environmental point of view. So scientists have been trying to find alternatives. And we, along other groups, of course, in the world, we have in recent years studied this possibility of using light emitting electrochemical cells, which are devices which have a lower number of layers compared to OLED, and particularly important is they use ionic metal complexes as luminophores, which are the largest majority, and they also serve as to help the charge transport in the device. So it is possible to implement these technologies, and the typical materials that are used are iridium complexes of the general structure indicated here, okay? The structure is the following. You have two cyclometallating CN ligands, and you have an ancillary neutral ligand, so the overall charge is 1+. And what is nice with iridium is that by changing the skeleton of the ligand, you can change the HOMO-LUMO gap and get any color across the visible palette, from the blue to red. And so, let's say, iridium is fantastic in this regard, and it is unique. And we use the iridium complexes to show within a European project that it is possible to make demonstrator of this technology that one day might complement the OLED technology. However, there is a problem. Iridium is great, but iridium, unfortunately, is the rarest element on the Earth's crust. And it's a kind of joke of nature, but it's so. So the world iridium production is 4 tons per year, so it is probably not reasonable to plan an illumination of the planet with iridium. And that's why in our group we proposed even already a few years ago to look at another part of the periodic table, and particularly to these D10 metal complexes of full D electronic configuration. But 2 of them are toxic, cadmium and mercury. 2 are very expensive, so only copper and zinc are left. And that's why we have studied for a long time copper complexes, and in this slide I try to summarize in a very simple way the work of maybe 20 years. And we showed by changing the ligand of the copper complex that we can move the emission from the red to the green to the blue. But the stability and the yield is not always optimized. So we are still far from the iridium performance. Another recent example is this dinuclear cluster-like copper-1 complex with the P and N ligand on the same unit. And we have a very high photoluminescence quantum yield, which is, for copper complexes, is interestingly high. And more recently, we have also explored trigonal geometries through pseudo-rotaxane, which give very strong structures and very high intensity of emission. So let's go back now to a consideration about energy. Perennial energy is overabundant. And because we have an extraterrestrial input from the sunshine of thousands of times our need. We can even say that even human ingenuity is high. If we have a problem, we can replace it. You know, if there is a problem with iridium, we can try to replace it with copper, for example. But resources of planet Earth are limited. And, this is a key point, a key message for today, the converters of solar energy are made of terrestrial stuff. So solar energy as such is not of very big use. We need converters, a few of them are indicated here, and they are made by digging the planet, okay, by mineral resources. So let's not say, okay, we have plenty of sunshine, the problem is solved. No, because there is always a bottleneck, which is the resources of planet Earth. And the rare elements in the energy technologies are many. I indicated some of them here for some of the technologies. You know certainly all of them. So we have this problem. So one can say, can we replace them? Unfortunately not. There is a very interesting paper in press on PNAS showing the replacement, the so-called periodic table of substitute performance of metals. And there is a substitute performance scale from blue to red. Blue would mean that you can have replacement for any application of that element. There is no blue on the table, you see, no blue, but there is a lot of red. So many of these elements are not replaceable with the present technology, and this is a problem that chemistry has to face. And so the only solution is recycling, but the rate of recycling of metals right now is miserable. Most of the metals are not recycled at all, and this is totally unacceptable, and this is something that chemistry has to work on. And now I will take a very few minutes to make some reflections on Europe at the end of this talk. And I'll try to convince you that the energy transition is an extraordinary opportunity for us. Why? The European Union has very little resources of reserves of hydrocarbons, 0 point something, a little bit of coal and no uranium. So we have to be aware that we enjoy the best quality of life on the planet in Europe, but our viable prosperity is based on energy resources coming from other continents. What about metals? We are in the same situation. We almost totally depend on imports. These are some key technological metals. One can say, okay, we have a lot of copper. No, we don't have copper. We are just recycling copper. That's why only 50 we use it. Okay, so we have started it. So what about all the rest of the materials? This is the import-export of Europe towards the rest of the world. And the arrows from Europe to the rest of the world are minimal compared to the sum of the arrows on the other direction. So we depend dramatically on imports. But we still have an advantage in one point that was already mentioned before by Professor Cole-Hamilton. We have an advantage of high added value manufacturing, including chemicals. Okay? So we are mastering this part of the story. It is the only one that is left to us. Let's not forget it. So if we compare fossils and renewables, it is very simple to conclude that this stuff here, they are stuff, the fossil are stuff. So either you have or you don't have. In Europe, we don't have. Renewable energy technologies instead are manufacturing and knowledge. This is what we have. And why this is manufacturing? Because solar, sunlight, and wind are impalpable entities. We have to convert them, and we have to manufacture them to convert them. And that's why we are strong in that field. That's why we have to pursue this and not that. So where we should possibly go? First of all, we have to increase the public awareness. There is a lot of energy ignorance across Europe, even though we target to be a knowledge-based society. And this is terrible. People have to be aware of what's looming ahead. We have to abandon fossil fuels before they will abandon us. I hope to have been clear on this. We have to stop the suicidal policy of cutting fund to education and research, because it is only through education and research that you can do the manufacturing and what I mentioned to you before. We have to favor the energy transition with adequate legislation. So we have to stop weakening the commitment to decarbonization of the economy, because it is against our interest. And this has been done recently. We have moderated our commitment. We have to realize that the energy transition is a huge opportunity, perhaps the only opportunity to save the European economy. Because the conventional recipes that have been applied so far for 6 years to revive our economy have failed. We know that every day on the newspapers. Why? Because we entered a new historical phase. What we have been shaped so far has been shaped by the fossil fuels, okay? But history goes on, and the fossil fuel age is in its final stage. What is desperately missing, I believe, is a bridge between scientists and decision makers. This is completely missing. So we are in a hurry, and without a bridge between knowledge and decision, the energy, climate, and resource crisis will probably overwhelm us. The energy transition has a lot of challenges and a lot of possible solutions that I try to summarize briefly today. I list some of them, and so you can go through my talk. And what we can say here, and we have to speak out outside, is that chemistry is at the root of the solution of these problems, and chemistry is essential for that. However, let's not lose the sense of limits as scientists. Through this picture here, these are the cleaning operation of the Louisiana coast after the Deepwater Horizon disaster. As you can see, there is no spatial robot or spatial machine capable of cleaning the marshes of Louisiana. The only thing you can do is to take your arms, to wear gloves, and to go there and by hands, meter by meter, and clean it up. This is the only solution. So we have to be aware as scientists that science and technology are not the solution to all of our problems. We need a lot of wisdom and also common sense. So let me conclude with coming back to the first slide. This is our energy timeline. This was my grandfather when he was born, 1903. This is me, and these are hopefully my grandchildren. So I think that this shows us that we are really, time for action is now. This period of time is very, very limited. So being up here gives to all of us and to our generation a big responsibility. And I would say that in the future, our generations will be ultimately judged in the future by the way that we live up to the energy challenge. Thank you very much for your attention.